Good afternoon, I am Mr. H. Thank you for joining me for this video where we understand the P series in a formal representation. You've seen this informally, except we didn't formalize it as a P series. Think about that video where we presented the comparison test. We always had something which looked like this, n was equal to a, and we had that infinity, a to infinity, anything from 1 over n to the p, where if p was greater than 1, we had convergence. But if p was less than or equal to 1, we ended up seeing divergence. This right here represented a good known standard which was proven to be convergent for these cases right here where p was greater than 1. You could see something like that, and you could say 1 over n square or anything which looked like this, p here being 2, is convergent. And this right here is a representation of what a P series is, because it depends on the value of P. A series that is dependent and affected by the value of P with regards to seeing convergence and with regards to seeing divergence. But we formalize it in this video. Examine the case over here. We will look at everything here just hypothetically for this specific instance. N equals 1. We'll evaluate the P series in terms of formal limits by means of 4 scenarios where P value can be less than 0, where P can be equal to 0, P is equal to 1, and P is greater than 1. You can do this limit evaluation for a P series function by these 4 routes, and I'll show you. And it's not hard. For the very first case here, p is less than 0, you're looking here, and this limit as n approaching infinity, you're looking at 1 over n to the p, but this p is really a minus p, because a minus p is less than a positive p, meaning it was less than 0. When you rewrite this, you're looking here at limit as n approaching infinity, n to the power of p. You know, as you evaluate this limit, infinity coming here to the power of a p value over here, you know you're going to have infinity over here, and you'll have a clear case of divergence. And we already know from here, from beforehand, that only this right here is your convergent case, this right here is your divergent case. You remember very well, if p was less than or equal to 1, it was divergent. If p was greater than 1, it was convergent. We're just showing that to be the case for each of these 4 scenarios. So this right here was your scenario 1, and it's shown you when you have a p equal to 0, look at this limit as n approaches infinity. We're looking here at n 1 over n to the power of p. When you put that p equal to 0, you have limit as n approaches infinity, you have 1 over n to the power of 0. What happens when you have 1 over n to the power of 0? Anything to the power of 0, other than we're looking at anything at the infinity side, but 1 over any number to the power of 0, a quantifiable number would be, you're looking at 1. You'd be looking at limit as n approaches infinity. You're looking at just this. This entire function becomes 1, and you know the value of that is 1. And this right here does indicate in divergence. It does not indicate convergence, because for any input x value coming here to your function, you're always going to get an output of 1. You're essentially looking at nothing other than a y equals 1 horizontal line. If you were to look at it from 1 up to infinity, and you were to do an improper integral for all of this area below the curve, you know it would be a divergent answer. But an improper integral by means of the integral test divergence leads to a series which is divergent. And you know that to be the case. And besides, if you're looking at this, it's nothing any different than a person looking at the first value is this, the next value is this, the next value, and the next value, all the way up to the infinite value. It's still always 1. You're never zeroing out, you're never decreasing. You have a continuous function. It's a positive function in terms of terms are positive, but it's never a decreasing function in terms of the values becoming smaller and going or tending towards 0. So this right here is a clear case of divergence. This next case, p equals 1, you're looking at 1 over n to the power of p. When you do the limit of this where p is equal to 1, everything becomes rewritten as limit as n approaches infinity. You're looking here at 1 over n. Anything which looks like 1 over n is an example of a harmonic series. If you were to open this up in terms of the terms, your terms would be 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4. It would be like a harmonic series going all the way up to 1 over infinity. But this, you know, is divergent. Remember, not too long ago in one of my earlier videos, I showed you how this could be assumed to be convergent because it is tending towards 0. It is continuous, but this value here and the value is close to the end. If you were to think about the basic test, you would say limit as n approaches infinity. This right here is tending towards 0. Yeah, it looks like it's tending towards 0. But if you were to start clumping things up or grouping them up, this is not group, this is not group, but you can group this. It's a value larger than half, but you can tone it down to half. You can do a bunch of other groups here. The sum of these would be greater than half, but you could bring it down to half. An arbitrary number of groups would still always give you values of half. Rather than tending towards 0 here, we're tending towards a half. An infinite number of halves in terms of their sums is still equal to infinity, and this right here would also be a divergent case, which is why everything over here is still divergent. The convergence will arise when the p-value is larger than 1. In that specific case right here, we have a limit as n approaches infinity. We have 1 over n to the power of p, where p is greater than 1. You can keep it exactly as this, and you can just assume that you're looking here in the end. With the infinity coming here, your series gradually increasing in terms of the n values, the n terms, and always having a value here p larger than 1 in terms of the p-value. You'll always end up having a scenario over here where you will tend towards 1 over infinity, and this right here is equal to a 0. I'm not saying that the sum of your series is equal to 0, but I'm saying you're tending towards a 0, and you'll see convergence in this case. You'll clearly see convergence because an improper integral of something like this with a p-value larger than 1 in terms of a relative graphic representation can look something like this from 1 up to infinity. This right here will be an area below the curve, which is a finite value. That finite value will indicate convergence. Therefore, your series will be convergent. But limit as n approaches infinity for a value here larger than 1. You will indeed see a function that will be made of positive terms and definitely tending towards a decreasing value of 0, a convergent case. Again, this is convergent, these are all divergent. What remains now in terms of understanding the p-series is just look at two good formalized examples and bring everything here into a good perspective. The first question we look at will be this: 1 divided by root n represents the rule or the function which is being evaluated from 1 to infinity. Is this series convergent or divergent? It's a good question. It will be continuous, and what we have to do is determine if it will work out in our favor as something which will be convergent. But you have a value here in terms of p. It's a p-series type of function, but it is going to be a p-value less than 1. And therefore, you know by means of that it's divergent. We just have to show it to be the case. But what would exactly your series look like? 1 over 1 plus 1 over root 2 plus 1 over root 3 plus 1 over root 4, 1 over root 5, and on up to 1 over infinity. You know it's decreasing, but is it decreasing such that is this entire function going to be a convergent case? When you look at it with regards to the very basic test, limit as n approaches infinity, this tends to look like it ends up being at 0, but do we have a convergence case? Hard to say. A convergence over here does not really, by means of the basic test, imply true convergence. We can do an integral over here, an improper integral from 1 up to infinity, 1 over n to the root power 1 over 2. We can look at it that way. If you want, you can do this in a formalized manner. Limit as t approaches infinity, you're looking here from 1 up to t, n to the power minus 1 over 2 dn. And then limit as t approaches infinity, you're looking here at n to the 1 over 2 divided by 1 over 2, n plus 1 divided by n plus 1. You remember that polynomial rule. T up to 1. You end up seeing 2 root n. You end up seeing from t up to 1. When you put the limit as t approaches infinity, you can have 2 root infinity minus root 1. And this will give you a value which is truly divergent in terms of the area below the curve. But this does not represent the sum of your series. This right here is not equal to that. But it does indeed tell you you have a series here which is divergent. But we knew that to be the case because p here was less than or equal to 1. Anyhow, we've shown it to you to be divergent. So this question here has been completed for you. The second one we look at is this: 1 divided by n squared plus 1 from 1 up to infinity. If you were to open this up, you're looking at something like when n is equal to 1, you have 1 over 2. When n is equal to 2, you have 1 over 5. N is equal to 3, you have 1 over 10. And last, when n is equal to 4, you have 1 over 17 plus all the way up to 1 over infinity. When you evaluate this by means of the basic test, you know it is approaching and tending towards 0, so it looks good and convergent based on that. But I want to evaluate it by means of an improper integral, and it would look something like this. And remember, we're doing this as a part of the integral test. You know that. 1 over n squared plus 1 dn. You can do a limit as t approaches infinity, and then we can bring in a t over here. Remember this: when you're looking here at a derivative of the inverse trigonometric function, you have 1 over 1 plus x squared. Therefore, by means of the integral, you should have that, the arctan. When I'm looking at this, I should develop an arctan, and it would be arctan n. But we'll be looking at it from this t up to 1. You can evaluate all of this without a calculator because it's easy. Arctan function in terms of graph is easy. You have a horizontal asymptote at pi over 2, y equals, and a lower horizontal asymptote at minus pi over 2. Your function looks something like this. Limit as this function approaches infinity, your value will approach this horizontal asymptote y equals pi over 2. When this comes in and this comes in, you're really looking at arctan of t, which is arctan of infinity. You're looking here at a pi over 2 minus arctan of 1. What angle is out there? If you were to do the tangent of it, you'd get a 1. The arctan of 1 would be right here, pi over 4. And you're getting here in terms of the area below the curve, and area below the curve to be pi over 4, but it's a finite value. This finite value represents series convergence, and it would truly be a convergent series. And you know you have over here a p-value larger than 1, and a p-series with a p-value larger than 1, it will be convergent. So this question has been completed for you, and this right here brings us to the end of this video where we are understanding the p-series. I presented you at the beginning the scenario where p-value was less than 0, p was equal to 0, p was equal to 1, and p was larger than 1. I didn't present you a scenario where p is less than 1 or equal to 1 but greater than 0 because there is no need. If this right here is divergent, this right here is divergent, that's divergent, and this is convergent, any value which would be less than or equal to 1 and including up to over 0, you know you can have divergence in between. So there was no need to even bring this in, but it would be divergent. Remember this. Have a good day. Thank you for watching. Bye.